On July 8, 2026, the journal Nature published a paper that headline writers immediately turned into something that sounds like science fiction. Physicists, the story goes, extracted energy from a black hole on a tabletop in a lab in New York City. A team at the Advanced Science Research Center at the CUNY Graduate Center, led by researchers including Hadise Nasseri and Andrea Alu, built a small ring of electronic components that amplified an electromagnetic wave using the exact physics theorists have attributed to spinning black holes for over 50 years. No actual black hole was anywhere near the lab. Nothing in the device physically spun. And yet the underlying mathematics, the theory that predicts how a rotating system can hand energy to a wave passing through it, held up perfectly. That is either one of the more elegant experiments in modern physics, or a headline stretched well past what actually happened. Let us sort the signal from the noise. Start with the 50-year-old idea this experiment was actually testing. In the 1960s and 70s, physicists Roger Penrose and Yakov Zeldovich separately proposed that a rotating black hole carries spare energy in its spin, stored in a region just outside its event horizon called the ergosphere. Penrose showed that, in principle, an object or a wave passing through that region could leave with more energy than it entered with, stealing a slice of the black hole's rotational energy in the process, and slowing the black hole down by a tiny amount. Zeldovich later predicted something similar could happen with ordinary rotating objects here on Earth. No gravity or event horizon required. As long as something was spinning fast enough relative to a wave bouncing off it. The catch, for 5 decades, is that nobody could build anything that spun fast enough to actually see the effect. It stayed a beautiful equation nobody had confirmed in a real device. Explain the workaround, because it is the clever part. The CUNY team could not spin anything anywhere near fast enough using an actual motor. So they built a ring of electronic resonators, small components that store and release electromagnetic energy, and rapidly switched their properties on and off in a precisely timed sequence around the loop. That sequence created a pattern that traveled around the ring, and to an electromagnetic wave interacting with the device. That traveling pattern looks and behaves exactly like physical rotation, even though every component in the ring stayed completely still. Physicists call this synthetic rotation. Feed a wave into that stationary but synthetically spinning ring, and the wave comes out amplified, gaining 7.8 decibels of strength with 0 moving parts. That number confirms the Zeldovich and Penrose prediction experimentally for the first time, using an electronic circuit instead of a space-time warping black hole. Consider what this actually unlocks. Beyond confirming an old equation, every amplifier in your phone, your Wi-Fi router, and your car radio depends on moving electrons through active components that need a power source, pushing energy in. This device demonstrates an entirely different way to strengthen a wave, using geometry and timing instead of raw power injection, and with no physical motion to wear out or fail. That is a genuinely new category of amplifier physics, not just a faster version of an old one. Engineers who build sensors, radar systems, or communication hardware care about this because a device with no moving parts is inherently more durable and can, in principle, be built at scales existing amplifier designs cannot reach. The Nature paper frames this as opening a new research direction: wave amplification through synthetic rotation. Rather than announcing a finished product, expect follow-up experiments chasing higher gain numbers well before anything ships in real hardware. Here is where the headlines run ahead of the physics. No black hole was involved in this experiment. At any point, And no energy was extracted from gravity, space-time, or anything resembling an astrophysical object. What the team actually built is an electronic analog, a device that replicates the wave mathematics of the Penrose and Zeldovich prediction using synthetic rotation, not a miniature black hole or a new power source. 7.8 decibels of gain, while a real experimental result is a modest amplification, roughly 6 times the wave's power, not some dramatic new energy supply. And the paper itself describes this as a proof of concept for a new amplifier architecture, not a working product. Practical applications in radar, sensors, or communications are still speculative and years of engineering away, since a single lab demonstration says nothing yet about cost, reliability at scale, or whether the effect holds up outside a controlled resonator ring. Treat this as confirmed physics, not confirmed technology. Quick recap. A CUNY Graduate Center team built a ring of electronic resonators that used synthetic rotation to amplify an electromagnetic wave by 7.8 decibels with 0 moving parts, experimentally confirming a 50-year-old Penrose and Zeldovich prediction about rotating systems and wave energy. Published in Nature on July 8. So, signal or noise? Signal. On the physics. This is a real, rigorously tested confirmation of a genuine theoretical prediction. And it does describe the same underlying math that governs how spinning black holes could shed energy. Noise. On the framing that scientists extracted black hole energy in a lab. Since no black hole, no gravity, and no astrophysical energy was anywhere in this experiment, only an elegant analog circuit. Watch for follow-up papers pushing the gain higher. That is the number that will tell you whether this becomes a real amplifier technology or stays an elegant physics demonstration. Subscribe for the science headlines checked against the actual paper. Signal from the noise. Every week.